This code uses a machine learning approach to predict future prices of the BOSPA index using the Arima model. It imports necessary libraries and downloads historical data, selects relevant columns, splits data for training and testing, and uses the Arima function to find the best Arima parameters. The model predicts future prices and adds them to the test dataset before adding them as a new column. However, it does not evaluate the accuracy of the forecasts. This code snippet uses Python and Matplotlib to visualize time series data and forecasts. It creates a figure with specific dimensions and plots 3 sets of data: training data, test data, and forecast on the figure. The training data and test data are closing prices from different datasets, while the forecast represents predicted values from the test dataset. The code also includes a line for adding a confidence interval to the plot. If needed, the plot is titled and labeled with axes and a legend for clarity. To view the plot, the show function is used. A Python code is evaluating a forecasting model's performance by comparing the actual and predicted closing prices in a test dataset. The mean squared error maze is calculated and then converted into the root mean squared error RMS. The RMS value, labeled as GRU model RMS, is printed, suggesting that the forecast was made using a model with gated recurrent units. Lower RMS values indicate better model performance in predicting closing prices. A function in Python is introduced to find the mean absolute percentage error mate between 2 sets of values, the actual and predicted values. This is done by first finding the absolute percentage errors, taking their average, and multiplying by 100 to get the value in percentage. The function is then applied to a group of test data, close values and their corresponding forecasted values from an Arima model. The final mate value is displayed on the console with 2 decimal points precision, indicating the accuracy of the model's forecasts in percentage. This Python code snippet defines a function called calculateMaze that calculates the mean absolute error made between 2 input datasets, a true values and spreaded values. It does this by finding the absolute differences between each corresponding value and then taking the average, resulting in the MA. The function then returns this value. The rest of the code uses the calculateMaze function to calculate and print the MA for a specific Arima model's predicted values. The MA value is stored in a variable called ArimaMaze and is printed in a formatted string with 2 decimal places. This code snippet utilizes a Python function called calculateMaze to determine the mean absolute scaled error maze, a metric used to evaluate the accuracy of a forecasting model. The maze is calculated by dividing the mean absolute error MA of the model by the MA of a baseline model. The snippet then uses this function to calculate the maze for an Arima model using a given MA for the model and a predetermined MA for the baseline model. The resulting maze value is stored in a variable and printed to the console with a label identifying it as the maze for an Arima model. This code combines an Arima model with an LSIM neural network to forecast time series data. The residuals from the Arima model are normalized and used as input for the LSIM network, which has 2 LSIM layers and a single dense output layer. The LSIM model is trained with an atom optimizer and mean squared error loss function, and then used to predict residuals on a test dataset. The predicted residuals are denormalized and compared to the actual residuals from the Arima model. A legend is added to clearly distinguish between the 2 sets of residuals. This visualization helps to evaluate the performance of the LSIM model in predicting the Arima model's errors. In this Python code, a previously trained Arima model is used for time series forecasting. The residuals are retrieved and normalized using a min-max scalar. A neural network model is then created using GRU layers, with a single unit dense layer for the final prediction. The model is trained with an atom optimizer and mean squared error loss function. The testing dataset is prepared and the trained model predicts the residuals. The predicted residuals are converted back to the original scale and compared with the actual residuals using Matplotlib. The resulting plot clearly displays the performance of the trained model in predicting residuals. A Python code is modifying a data structure called test, potentially a pandas data frame. It appends 2 new columns, forecast hybrid and forecast hybrid GRU. The forecast hybrid column is formed by taking the values from the existing forecast column and adding them with the flattened version of the residual LSIM data. Similarly, the forecast hybrid GRU column is created by adding the residual GRU data to the base forecast values. Essentially, the snippet generates two hybrid forecast columns in the test data frame by combining the forecast values with residuals from two different models, LSEM and GRU. These models are commonly used in predicting sequences or time series data in recurrent neural networks. This code snippet uses Python to create a plot for visualizing financial data, specifically closing prices and forecasting results. The plot shows the historical prices used for training a predictive model and the actual prices during a test period, as well as forecasted values from an Arima model. The code also includes inactive lines for plotting additional forecasts from different models. The plot displays an upper and lower confidence interval, visually representing the uncertainty in the forecast. It is titled Arima Forecast with 6-day lag and includes a legend for easy identification. This code defines a function, calculateMape, to find the mean absolute percentage error mate between two sets of values. MAPE measures the accuracy of a prediction model and is calculated by finding the average difference between the true and predicted values, divided by the true values, then multiplying by 100. The function is used to calculate MAPE for two forecasting models, comparing their predicted stock prices to actual values from a dataset named chest. The results are then printed out in a formatted string, showing the percentage errors up to 2 decimal places for each model. This Python code creates a function called calculateMace to compute the mean absolute error made between two sets of data true values and predicted values. The MAE is obtained by finding the average of the absolute differences between the two sets. The function is then used to calculate the MAE for two different sets of predictions, forecast hybrid and forecast hybrid GRU, compared to the true values from a test dataset. The resulting MAE values are printed to the console, rounded to 2 decimal places. Lower MAE values indicate more accurate predictions for the closing prices. The below Python code defines a function, calculateMace, which calculates the mean absolute scaled error MAEs by taking in the MAE of a predictive model and comparing it to the MAE of a baseline model. The code uses this function to calculate the MAEs for two specific models, an Arima model and an Arima with GRU-gated recurrent unit model, with a fixed baseline MAE of 15,143.23. The MAEs values for each model are then printed with a precision of 2 decimal places, showing how well each model compares to the baseline. A lower MAEs indicates a better predictive performance. Two hybrid prediction models, combining LSEM or GRU neural networks with Arima models, are compared by calculating the mean squared error MAEs between their forecasted and actual closing values provided in the test dataset. The MAEs values are then converted to root mean squared errors RMS, a commonly used measure of regression model accuracy. The RMS values are printed for comparison, with higher values representing lower accuracy and lower values indicating higher accuracy. This Python code uses the Finance library to retrieve historical financial data from Yahoo Finance for the BOSPA index. The data is filtered to show only the closing prices within a specific date range, and the length of the modified dataset is calculated. The Python code is used to plot time series data and corresponding predictions using a library like Matplotlib. It follows these steps. 1. It retrieves time indices from two different datasets and stores them in separate variables. 2. It then creates a new figure with a specific size. 3. The figure plots 3 lines, one for the actual closing values from the training dataset, one for the testing dataset, and one for predicted values. 4. The title suggests that the predictions were made using a LSEM model, but the label indicates Arima was also used. 5. The X and Y axis labels represent the data being plotted. 6. A legend is added for clarity. 7. Finally, the figure is shown on the screen. This code is meant to visually compare the model's performance in predicting stock prices using LSEM and Arima methods. This Python code snippet implements a process for normalizing and modeling time series prediction residuals, which it then plots. The steps involved include extracting the residuals from an Arima model, normalizing them using a min-max salar, building a GRU model with 2 layers and 50 units each, preparing and training the model, preparing testing data, using the model to predict future residuals, and plotting the actual and predicted residuals over time. The graph produced uses a plotting library and includes a legend to differentiate between the two sets of residuals. The code performs the following steps. 1. Extracts the residuals from an Arima model. 2. Normalizes the residuals using a min-max seller to have values between 0 and 1. 3. Creates a LSIM neural network model using keras. 4. Adds 2 LSIM layers and 1 dense layer to the model. 5. Compiles the model with an atom optimizer and mean-squared error loss function. 6. Reshapes the normalized residuals for the model's input. 7. Trains the model for a specified number of epochs and batch size. 8. Prepares a test set for evaluating the model's performance. 9. Predicts the residuals on the test set using the trained model. 10. Scales the predicted residuals back to the original values. 11. Plots the actual and predicted residuals for comparison. In conclusion, the code uses an LSIM model to predict and visualize the residuals from an Arima model. The following Python code alters the data frame forecast by adding 2 new columns. Forecast hybrid and forecast hybrid grew. These columns are computed by taking the values from the existing forecast column and combining them with 2 sets of residuals. One from an LSIM model residual LSIM and another from a GRU model residual SGRUSH. To ensure proper alignment with the forecast values, the DNP function is used to horizontally stack the residuals. This results in 2 hybrid forecasts that incorporate adjustments from different neural network models. This Python code evaluates prediction models by calculating the RMS between actual and predicted financial closing prices. 3 different RMS calculations are performed, but the last print statement is misleading as it suggests a GRU model, when in fact it corresponds to a basic Arima model. The 3 RMS results are then printed, with lower values indicating better model performance. This code snippet defines a function called calculate-map, which computes the map between actual and predicted values. The map measures prediction errors as a percentage of the actual values and is used to evaluate 3 different models: Arima with a hybrid approach, and Arima with a hybrid approach incorporating a GRU. Each model's map is calculated by comparing predicted closing prices to actual closing prices for a financial instrument. The resulting map values are printed, with a small error in the labels. One of the print statements should refer to a different model, possibly a plain Arima model without the hybrid or GRU enhancements. This Python function calculates the mean absolute error made between 2 sets of values, actual and predicted. MA is an indicator of prediction accuracy in a regression model, representing the average absolute difference between predicted and actual values. It takes 2 parameters, true values and predicted values, representing observed data and corresponding predictions. After computing the absolute differences, the function takes the mean to determine the MA. The code then uses this function to calculate MA for 3 different sets of predictions against the actual values from the dataset databudist. The MA values are stored in variables labeled according to the model used. However, there is an error in the print statements, all labeled as Arima model MA. Even though they correspond to different models, this could be due to a copy-paste mistake that needs correction. This code snippet showcases a Python function, calculate-maze, that finds the mean absolute scaled error maze for a given model. This function takes in 2 inputs: a model maze, the mean absolute error for the forecast model, and baseline maze, the mean absolute error for a simple baseline model. Maze is obtained by dividing the model's MA by the baseline's MA, providing a measure of the model's accuracy in comparison to the baseline. The snippet then uses this function to calculate the MAs for 3 different models: Arima, and Karimag, using their respective MA values and a fixed baseline MA of 1330. The resulting MAs values are then printed, correctly rounded to 2 decimal places. However, an error is present in the print statements, with the labels for Sharemat and Sharema being the same, indicating a possible mistake during copying and pasting. It is essential to use the correct model names to ensure proper labeling of the MAs values. This Python code is used to plot stock price data. It first assigns the date indexes for the training and testing datasets to variables. Then it creates a figure with a specific size for plotting. The training data is plotted in blue with a dotted line, while the testing data is plotted in orange. A separate set of data representing predicted stock prices from an Arima model is plotted in green. The title of the plot incorrectly states it's from an LSIM model. The x-axis is labeled as date and the y-axis is stock price. A legend is included to distinguish the different data sets. The plot is displayed for visual analysis. This Python code combines Arima and GRU models to analyze and predict time series data. Firstly, it takes residuals from a fitted Arima model and scales them using min-max scalar. Then, a neural network model with GRU layers is constructed for regression or single-step forecasting. The neural network is trained using Atom optimizer and mean squared error as the loss function, and then used to predict residuals from a test set. The predicted residuals are transformed back to their original scale and compared to the actual residuals on a chart, assessing the effectiveness of the GRU model in predicting the Arima model's residuals. This approach of combining linear and nonlinear models can improve time series forecasts. This code uses a combination of Arima and LSM models. It first extracts residuals from an Arima model, normalizes them, and uses them to train a sequential LSM neural network. The LSM model is compiled with the Atom optimization algorithm and mean squared error as the loss function. After training, it uses the model to predict residuals for a test dataset and plots a comparison between the actual Arima residuals and the predicted LSM residuals. The code is altering the Fourier-Stiff data frame by introducing two new columns. The purpose is to improve time series forecasting by combining a base prediction with residual values from different machine learning models. The first line adds a column called forecast hybrid by using values from the forecast column and adding residuals from the residual LSM variable, representing the discrepancies between observed and predicted values from an LSM model. The JIMP function is used to ensure proper formatting. Similarly, the second line adds a forecast hybrid GRU column by including residuals from the residual GRU variable, representing errors from a GRU model. This results in another hybrid forecast that accounts for systematic errors captured by both models. Ultimately, the code aims to refine forecast values in Fourier-Stiff for better accuracy in time series forecasting. The Python code snippet evaluates the performance of forecasting models by calculating the root mean squared errors between actual and predicted stock closing prices. It does this for three different models: Arima, a hybrid of Arima and another model, and a hybrid of Arima and a GRU neural network. The snippet then compares the RMS values of each model to determine which one gives more accurate predictions. The code uses a function called JALULATE-MAPE to calculate and print the mean absolute percentage error MAPE for different sets of predictions. This function takes in two lists or arrays of values, one containing the true values and one containing the predicted values. Inside the function, the absolute percentage difference between each true and predicted value is calculated and then averaged to obtain the MAPE. The MAPE is then converted into a percentage and returned as the final result. The code then applies this function to three different sets of predictions and prints out the MAPE value in a formatted string. There is a typo in the print statement where the label Arima model MAPE is repeated, likely meant to show each distinct model's MAPE. This code snippet in Python defines a function called JALULATE-MAPE, which calculates the mean absolute error MAPE between two lists, the true values and the predicted values. The MAPE measures the accuracy of predictions for continuous variables by finding the average absolute difference between each true and predicted value. It is then used to calculate the MAPE for three different sets of predictions: forecast hybrid GRU, and forecast, comparing these predictions to the true closed values from the JDataWidest dataset. The resulting MAPE values are printed to the console, with the results rounded to 2 decimal places. However, it appears there may be a mistake in the code, as all of the print statements say Arima model MAPE even though they refer to potentially different models, such as one with a GRU neural network. This could be an oversight or error in the provided code. The given Python code creates a function called JALULATE-MAPE that uses the mean absolute error MAPE of a predictive model compared to a baseline model to calculate the mean absolute scaled error MAPE. The function requires two inputs: the MAPE of the predictive model and the MAPE of the baseline model. The code then uses this function to calculate the MAPE for three different models, taking into account a baseline MAPE value of 1234. The resulting MAPE values are then printed with 2 decimal places. These models are titled Arima and Arima with a GRU extension, which may suggest the use of a gated recurrent unit in the latter. However, there is a small error in the code where the first print statement writes JARIMA-MAPE instead of JARIMA-MAPE, assuming the model's labels correspond to their variable names. The code snippet downloads historical stock market data for the BOSPA index from October 18. 2023 to November 9, 2023 using the GIF download method from the eFinance library. It then filters the data to include only the close column, representing the index's closing price for each trading day. Finally, the length of the resulting dataset is calculated using the length function to determine the number of successful trading days within the given date range. This Python code makes predictions for future time periods using a forecasting model. The model returns predicted values and confidence intervals, which are saved as forecast and then converted into a new data frame called forecast. This new data frame has the same indexing as an existing data frame called datatwist. Ensuring alignment with its dates or periods, the predictions are stored in a column named forecast and can be analyzed or compared with actual values. This code creates a graph displaying stock price data and predictions. Using Python, it assigns time series indices from two datasets to separate variables, creates a 12x6-inch plot and plots 3 lines representing actual and forecasted stock prices. The plot title suggests the use of a LSM model, while the X and Y axis labels are set to date and stock price, respectively. Additionally, it includes a legend and displays the plot. This Python code snippet combines Arima and GRU neural network models for time series analysis. It begins by taking the residuals from an Arima model and normalizing them with min-max Salar. Then, a GRU model is created with 2 layers and trained with selected hyperparameters. The model is then used for testing and prediction, and the results are visualized with a line chart. The ultimate goal is to enhance Arima predictions by using a GRU network to capture any overlooked patterns in the data. This snippet of Python code prepares data from a previous Arima model for input into a long short-term memory LSM network. This process involves obtaining residuals, normalizing them using a min-max Salar, and reshaping them to fit the LSM model's required input format. The model consists of 2 LSM layers and a dense layer for output and is trained using the normalized residuals as both input and target data. After 300 epochs, the model predicts the residuals of a test dataset and transforms them back to their original scale using the same Salar. The original and predicted residuals are then plotted on a graph using the matplotlib library for comparison. This code manipulates a data frame in Python called forecast, creating 2 new columns named forecast hybrid and forecast hybrid GRU. These columns contain the sum of the values from the forecast column and residual values from variables residual SLSM and residual SGRUSH. The GIMP hestash function is used to prepare the residuals for addition. This snippet essentially combines predicted residuals from LSM and GRU models with the original forecast values to generate 2 new hybrid forecast sets within the data frame. This Python code calculates the root mean square errors for 3 forecast models' predictions compared to actual closing prices. It uses a function from a machine learning library to calculate the mean squared error between the actual and predicted values for each model. These errors are then stored in separate variables. The code then prints out the RMs for each model by taking the square root of the mace values. However, there may be some confusion in naming conventions, as the variables may not match up correctly with the models they represent. The function calculate finds the mean absolute percentage error between predicted and true values in a dataset. It first calculates the absolute percentage error for each prediction, followed by the mean of these errors. The result is then multiplied by 100 to convert it to a percentage. This is applied to 3 sets of predictions named forecast hybrid, and forecast hybrid GRU, using the closed values from the datatwist data frame. The MAPE values for Arima with hybrid adjustments, and Arima with hybrid GRU are printed, with small formatting errors. The code snippet provided defines a function, calculate that measures the mean absolute error made between 2 lists of values, the actual and predicted values. This is a commonly used statistical measure to determine the accuracy of a forecasting model, by calculating the average of absolute errors between the predicted and true values. The function is then utilized to find the MA for 3 different forecasting scenarios. Using data from a data frame of forecast and a variable forecast associated with a basic Arima model, each MA value is rounded to 2 decimal places and presented with a descriptive message specifying the model it corresponds to. However, there seems to be an error in the print statements as they all display the same message. Arima model may causing confusion. It is likely that each print statement was intended to include a unique identifier for each model. This code snippet uses Python to calculate and print the mean absolute scaled error maze for 3 predictive models. Maze is a measure for evaluating the accuracy of a model compared to a naive baseline. It has a function, isolate_maze, which takes 2 arguments, may of the model and may of the baseline, and returns their ratio. The code then computes the maze for 3 different models and prints them, each divided by a fixed baseline may of 1285, 27 and formatted to 2 decimal places. However, there may be some errors in the code, including a possible duplication of the Arima model's maze and a discrepancy in naming conventions for the Arima with modification model.